Hello and welcome to all students. This is SYBSc Semester 4 class, paper number 1, Calculus 4, unit number 3, beta and gamma function. So in the previous lectures we studied about a gamma function or gamma integral. Now today in this lecture we study about a beta function. Okay, so first of all we define what is beta function. Write the definition. The definition is that a beta function of m comma n is defined by, it is denoted by beta mn and defined as beta mn is equal to integration over 0 to 1 x raised to the power m minus 1 into 1 minus x raised to the power n minus 1 dx. M is greater than 0 and n is greater than 0. So this is the definition of beta function. Okay, so once again, a beta function of m comma n is denoted by beta m comma n and defined as beta m comma n is equal to, it is integration over 0 to 1 x raised to the power m minus 1 and 1 minus x into bracket 1 minus x raised to the power n minus 1 dx, provided that m is strictly greater than 0 and n is strictly greater than 0. The beta function is also called as Euler's integral. The beta function is also called as Euler's integral of first kind. Euler's integral of first kind. Okay, so keep this in mind. Now we write one note about this beta function, and note that beta function of negative number is not defined. Okay, so beta function of negative number is not defined. Now next we try to prove some properties of beta function. Okay, now our next point of this lecture is properties of beta function. Okay, properties of beta function. Properties of beta function, and the first property of beta function is beta mn, beta m comma n is same as beta n m. Okay, so this is our first property of beta function, and we try to prove this property. The proof is very simple. Okay, so to prove this property, let us start from left hand side. Okay, consider the LHS and LHS of this equality is beta m comma n, and by definition of beta function or beta integral, the beta mn is nothing but integration over 0 to 1 x raised to the power m minus 1 into 1 minus x raised to the power n minus 1 dx. Okay, so this is the definition of a beta function, and in this integral let us use substitution. Substitution is that instead of 1 minus x, let us put variable y. Okay, so therefore for so therefore this will implies minus dx is equal to dy, or we can write dx is equal to minus dy. Okay, now we use due to substitution. We get now the limits of old variable x limits are 0 to 1, and due to this substitution we have a new variable y, and limits of new variable y are, see here, if I put x is equal to 0, then y becomes 1, and if I put x is equal to 1, then y becomes 0. Okay, so again we write after substitution, the left hand side becomes like this: LHS is equal to integration over 1 to 0. Now instead of x I will write, I will write 1 minus y raised to the power m minus 1 into, instead of 1 minus x, write y raised to the power n minus 1, and instead of dx write minus dy. So if we reverse the sign of this integration, this negative sign will get cancelled. So integration over 0 to 1, and y raised to the power n minus 1 into 1 minus y raised to the power m minus 1 into dy. Okay, so this integration is nothing but the beta integration, beta n m. Okay, and this is equal to RHS of the given equality. Thus we have proved, beta m n is always equal to beta n m. Okay, so this is the first property. This is the first property of the beta function. Okay, let us go to the second property of the beta function. Now let us try to prove the second property of beta function, and the second property is beta mn is equal to 2 times integration over 0 to pi by 2 into integration of sine raised to the power 2m minus 1 theta into cos raised to the power 2n minus 1 theta d theta. Okay, so this is the second property of beta function, and it says that beta mn is equal to 2 times integration over 0 to pi by 2 sine theta raised to 2m minus 1 into cos theta raised to 2n minus 1 d theta. Okay, so let us write the proof. So by definition, we start from definition. Definition of beta mn is equal to integration over 0 to 1 x raised to the power m minus 1 into 1 minus x raised to the power n minus 1 dx. So this is the definition of beta function, and in this definition we make some substitutions. Okay, and these substitutions are, so instead of x we put sine square theta. So due to this substitution, what we have is therefore dx will be 2 times sine theta, and derivative of sine theta is cos theta d theta. Okay, so instead of dx I will write this term. Okay, and due to substitution we have a new limit, new variable, and limit of this new variable we find here. Okay, our old variable is x and its limits are 0 to 1, and new variable is theta. Now we try to find the new limits of this variable. Therefore what we have is square root of x is equal to sine theta. Okay, so when x is equal to 0, theta is also equal to 0, and when x is equal to 1, theta will be pi by 2. Okay, 0 to pi by 2. Okay, due to this substitution we get, so if I use this substitution in our definition of beta function beta mn, so integration becomes like this: 0 to pi by 2, and instead of x we are writing sine square theta. Therefore it will be sine 2m minus 2 theta, and instead of 1 minus x means 1 minus sine square, and it is cos square, and cos raised to the power 2n minus 2 theta, and instead of dx is nothing but 2 sine theta into cos theta d theta. It is equal to, so constant is 2 outside integration, or I can write like this: beta mn is equal to 2 is a constant outside integration over 0 to pi by 2 into sine. Now the power of sine will be 2m minus 2 plus 1. Okay, so it will be 2m minus 1 theta into cos raised to 2n minus 1 theta d theta, and this is the second property of beta function, and we have proved that second property. Okay, now this is the end of this lecture, and remaining properties we will prove in the next lecture. Thank you very much for paying attention.